This is the second set of slides for the biochemistry unit. This is focusing on water and the fitness of the environment. Keep in mind that we talked about just like general chemistry in the first slides. That should be a lot of review. If you do need to go over it, I can send out that PowerPoint, but I'm not going to do a video on it. When we look at water molecules, and this should be review as well, we know that water is a biological medium for all life. We're made up of a ton of water, and without it, we can't survive. Um, it is formed between polar covalent bonds, which are between the hydrogens and oxygens in a single compound. And then we have hydrogen bonds that attract each molecule to the other molecule. And that is why we get such special properties from water. Almost all cells are surrounded by water, and they are always over half water themselves, and the abundance of it on Earth makes it habitable. Any other planets, one of the big reasons why we can't go to other planets and live there is the lack of water. There are 4 properties due to the hydrogen bonds in water. We see cohesive and adhesive behavior. Water adheres to itself as well as anything else that is polar. Water's ability to moderate temperature, so it takes a long time for water to boil because it can basically collect a lot of energy. It can be what we call a heat sink. Basically, we can keep applying heat and it will absorb it and not change its properties. Water also expands upon freezing, and it is a solvent, which means it dissolves in many substances. What causes these water molecules to cohere and adhere? Specifically, are intermolecular forces or hydrogen bonds. So if we look back, we see that this bond is an intermolecular force or a hydrogen bond. And so they're not physically bonded, this can break, but they are attracted to each other. Cohesion is when water molecules stick to each other. It happens all the time. And then adhesion is when water sticks to other substances. The most common one we see is in plant cells. This is how water gets from the roots to the top of the tree. It's working against gravity, but because it can adhere to itself and to the sides of the xylem and phloem, it can travel upwards. We also see that this creates surface tension. And basically, we see that cohesion allows for certain things to sit on top of water. Again, this is hydrogen bonding causing this. The second property, temperature moderation, the way that this works is that water has a high heat capacity, right? We talked about the idea of a heat sink. The idea that it requires a lot of energy to raise the temperature of 1 gram of water. It means that water can absorb huge quantities of heat without a lot of change to its own temperature. We call it a thermoregulator. Why? Hydrogen bonding again. These 2 hydrogen bonds are very strong, and so all of the green dotted lines are my hydrogen bonds. They're super strong, and only when they break do we see a change from water to gas. And again, remember that bonds breaking and forming have to do with energy. Water is really good at absorbing that energy. Why is this important? When it comes to water in the air, when it comes to oceans, they are very good at absorbing heat, which allows our planet to regulate its temperature. If there was nothing absorbing this energy, we would have huge fluctuations in temperature. This is also why we in Lynn, or when I used to live in Marblehead or in Boston, we don't get as much snow as something as a town in Central Mass where my parents live, because the ocean acts as a heat sink. Basically, it absorbs a lot of the heat from the sun, and then that means that it keeps the coastal areas a little bit warmer in the winter and a little bit cooler during the summer. And so we don't see as severe temperature fluctuations because a lot of energy is being absorbed or released by the ocean. And so that's why we see that. Again, the high specific heat can be traced to those intermolecular forces. Heat is absorbed when hydrogen bonds are broken. Heat is released when they are formed. The high specific heat of water minimizes the fluctuations to permit us to basically live. If bonds were breaking all over the place, we would be dead, basically. If we take a look at a little bit of data, this kind of addresses the idea of thermoregulation, what I was talking about with the oceans. Feel free to pause this and kind of look at it if you'd like to. Another reason that this is so important, this idea that it has high specific heat, is the heat of vaporization, the heat required to become vapor, and the heat required for water to condense back to liquid is very high. And so this allows evaporative cooling to help us become very stable. Last trait, water expands upon freezing. We see that the ice creates these like very crystalline structures. The hydrogen bonds become firm. And so instead of being kind of fluid, we see that it expands to be larger. This is why if you have water in your pipes and it's very cold and they freeze, they can make your pipes explode. This is also why ice floats, because it is less dense, because there's more space between the molecules. So it expands during water, or it expands during freezing. When I have to pause this video, I get lost. Again, it expands during freezing. That means that it's less dense than liquid water. It also means that it is, so it'll float. It also means that it's going to expand to fill a certain space. The last property of water that is really important for us to know is that it is a solvent. It means that in a solution, which is a mixture of substances, the solvent is going to be the dissolver and the solute is the dissolvee. An aqueous solution is one in which water is the solvent, and there are hundreds of aqueous solutions. Water is a highly versatile solvent. This is because it's polar, which means that the partial positive and partial negative on the water molecules are going to pull other compounds apart. So salt is an ionic compound. That bond is very strong, but the positive sodiums and the negative chlorines will be pulled off of the salt crystalline structure and dissolved in water. Each ion is surrounded by a sphere of water molecules. We call it a hydration shell that isolates it from Dee, don't do that. Dee, stop. Guys, my boyfriend's dog is currently eating trash. Stop. So it's called a hydration shell. And it allows those ions to stay isolated and not become solid again. Even larger polar molecules, such as proteins, can be dissolved in water if they have ionic or polar regions. If you think back to what we learned in class, we have those partial positive and partial negative spaces on the molecules, and they will attract to anything that is also partially charged. This brings us to talking about hydrophobic and hydrophilic, which are related to cell structures. Hydrophilic substances are ones that have affinity or are attracted to water. Therefore, we can assume they are polar. A hydrophobic substance is one that does not have affinity for water, or it fears water, it repels it. These are usually fats, lipids, oil molecules, which are hydrophobic. A colloid is a stable suspension of fine particles in liquid, like milk, fat suspended in water. Basically, this means that the oil molecules are only slightly hydrophobic, so it will dissolve in water, whereas something that is totally hydrophobic will make that layer of oil on the top of water, like a salad dressing or like when you make a soup and the fat rises to the top. When we're talking about water, we also have to talk about acids, bases, and buffers, and because they contribute to whether or not we are able to live. When we look at water, we have our water molecules. Those water molecules can interact and they can form two different molecules, hydronium and hydroxide. Depending on how much hydronium and hydroxide are present in the water, you're going to get an acid or a base. Usually when there are equal amounts of hydronium and hydroxide, you're going to have a pH of 7, which is why water has a pH of 7. When the molecules with the extra protons are hydronium ions or H plus ions, you're going to get something that is highly acidic, whereas if you have a larger concentration of hydroxide ions or OH negative ions, you're going to have a base. These molecules are floating around all the time in water, and so when we actually describe water as H2O molecules floating around, that is inaccurate. It's usually a combination of H2O molecules, hydronium molecules, and hydroxide molecules. Um, in water, if we go back, the hydroxide and hydronium should stay consistent. Random dissociation of water molecules is really rare. If that happens, that's going to impact the chemistry of the cell, which is going to be a huge problem. Concentrations of H and OH are equal in pure water. When we add things to our water, the concentrations of H and OH become modified. We use a pH scale, 0 to 14, or 1 to 14, 1 being highly acidic, so lots of hydrogen ions, 14 being very basic, lots of OH ions. Again, this kind of summarizes what we were talking about. When we talk about buffers, and something to remember is that highly acidic substances are equally as dangerous as very basic solutions. Bleach is a very basic solution. Hydrochloric acid, very acidic solution. They are both very corrosive. A lot of the time, we kind of are duped into thinking that one is more corrosive or dangerous than the other. When we talk about buffers, the internal pH of most living cells has to remain close to 7. And buffers are substances that resist changes in concentrations, which is what we want in the human body because we don't want our pH fluctuating all the time. When your pH changes, that's where you get all sorts of issues. Most buffers consist of an acid-base pair that can combine with hydroxide ions. When we think about buffers in action and in biology specifically, when we burn fossil fuels, this starts to threaten water quality. Specifically, it impacts the pH of the water. CO2 is the main product of fossil fuel combustion, and therefore about like 25% of human-generated CO2 is absorbed by the oceans. CO2 dissolves into the ocean, it forms carbonic acid, and then it starts to produce acids in the ocean. We call it ocean acidification. This is a big problem. As the seawater acidifies, hydrogen ions combine with carbonate ions to produce bicarbonate. Carbonate is required for calcification, and by many marine organisms, it is used when we're building reefs and things like that. And so we see that this is beneficial in some ways, but if it is not able to be transferred into something usable, the ocean becomes more acidic. The reason we need to think about this is that as we get rid of coral reefs, the processing of CO2 into calcium carbonate and into coral reefs is going to be really limited. Therefore, we just have a lot of acid floating around in the ocean. Another real life scenario that we need to think about is acid rain. The burning of fossil fuels also produces sulfur oxides and nitrogen oxides. These compounds react with water in the air to form really strong acids that end up falling as rain or snow. Acid precipitation is anything with a pH lower than 5.2. This damages lakes, streams, changes the soil chemistry, can be very corrosive. Case in point here. So as we're burning fossil fuels, we are adding more acid to our environment. This looks over the pH scale. Please pause this and look at this if you want to. Not super necessary. And this talks about how we calculate the actual pH. We take the concentration of hydrogen and hydroxide ions and we use a negative log. You will not have to calculate this on the AP test. Again, take a look at this if you want to. And that is the end of that.